When astronomers built the first models of how planetary systems form, they used the only example they had: our solar system. 8 planets, rocky ones close in, giant ones farther out. Everyone moving around the sun in the same direction. Everyone kept mostly to the same plane. Everyone, compared with what we would later discover, almost shockingly well behaved. It was a beautiful model. It was not wrong. It was just based on a sample size of 1. Then we started finding other planets, and the universe began humiliating us. The first confirmed planets outside our solar system did not orbit a normal star. They orbited a pulsar, a dead stellar core spinning more than 100 times per second. The first confirmed exoplanet around a sun-like star was not an Earth-like world in a gentle orbit. It was 51 Pegasi b, a gas giant so close to its star that its year lasted only about 4 days. A Jupiter where no Jupiter was supposed to be. After that, the catalog got stranger every year. Words that once sounded like science fiction: hot Jupiter, super Earth, mini-Neptune, sub-Neptune, lava world, ocean world, rogue planet, Hycean world, Chthonian planet, super puff, became ordinary language in planetary science. Astronomers were not just discovering more planets. They were discovering that the universe makes categories of worlds our solar system never warned us about. The solar system is not the template. It is one quiet page in a catalog that goes on for longer than we have yet read. This is that catalog. Not every footnote, not every borderline case, but every major kind of world the universe has taught us to take seriously. And it begins somewhere familiar. Rocky planets. Start here because this is home. Rocky planets, sometimes called terrestrial planets, are worlds with solid surfaces made mostly of silicate rock and metal. They have dense iron cores, rocky mantles, thin crusts, and atmospheres that are usually secondary, produced by volcanoes, impacts, chemistry, and time, not captured directly as huge envelopes from the young protoplanetary disk. In our solar system, they are Mercury, Venus, Earth, and Mars. They sound familiar until you look closely. Mercury is a burned and frozen airless rock. Venus is a runaway greenhouse with crushing pressure and a surface hot enough to melt lead. Mars is a cold desert with almost no air. Earth is the exception that makes the category feel safer than it is. Among exoplanets, rocky worlds appear to be common. Statistical studies of planets found by Kepler suggest that the Milky Way contains enormous numbers of small rocky planets, including billions that may orbit in the broad temperature range where liquid water could exist. But even here, the familiar category becomes unstable. A planet only slightly larger than Earth may still be a rock. A planet much larger than Earth begins to become something else. Above roughly 1.5 to 2 Earth radii, many planets appear to carry thick envelopes of hydrogen, helium, water vapor, or other volatiles. The line between a big rocky planet and a small gaseous planet blurs. Earth is not simply one example of a common thing. Earth may be close to the upper limit of how comfortably rocky a habitable surface planet can be. And if a rocky planet moves too close to its star, the rock itself stops behaving like rock. Lava worlds. Take a rocky planet and place it so close to its star that its orbit is measured in hours or days. The star fills the sky. Tides lock the planet, forcing one hemisphere to face the furnace forever while the other faces permanent night. On the day side, sunlight is not weather. It is geology. The surface melts. Mountains become fluid. Basalt becomes ocean. The ground becomes a glowing sea of liquid rock. On some of these worlds, the heat is so extreme that the surface does not merely melt. It evaporates. The atmosphere becomes a thin mineral vapor. Silicon monoxide, sodium, magnesium, iron, atoms, and molecules that on Earth belong in stone, now floating as weather. Winds carry this vapor toward cooler regions. It condenses. It falls. Rock rain. Mineral snow. A weather cycle made of the planet's own surface. Kepler 10b, COROT 7b, and the day side of 55 Cancri belong to this family of extreme close and rocky planets. Not all details are known. Their atmospheres are difficult to measure, their surfaces impossible to image directly. But the physics is clear enough. Put rock close enough to a star, and geology becomes meteorology. The ground becomes ocean. The ocean becomes sky. The sky rains the ground back down. Carbon worlds. Most rocky planets we know are built from oxygen-rich chemistry. Silicates, metal oxides, minerals similar in broad family to the rocks of Earth. But not every protoplanetary disk has the same chemistry. If a region of a disk contains more carbon relative to oxygen, the planets that form there could be built differently. Instead of silicate mantles like Earth's, they might contain more carbides, graphite, and under pressure, possibly diamond-rich layers. This is where the famous idea of a diamond planet came from. Not a polished jewel floating in space. Not a planet literally made entirely of diamond. A carbon-rich world whose internal chemistry could allow enormous amounts of carbon to be compressed into exotic forms. 55 Cancri has been discussed in this context, though its true composition remains debated. The important point is larger than one planet. Planetary chemistry is not required to repeat Earth. Change the ratio of elements in the birth disk, and the definition of rock changes with it. The universe does not make one kind of stone. It makes whatever the local chemistry permits. Ocean worlds. Move outward, past the lava worlds, past the inner furnace, into regions where water ice can survive during planet formation. There, planets can accumulate water not as a thin surface layer like Earth's oceans, but as a major structural component of the planet itself. 10% water by mass, 20%, perhaps more. Worlds where water is not a surface feature but a building material. The result is not necessarily a blue Earth with deeper seas. It may be stranger. A global ocean hundreds or thousands of kilometers deep. No continents. No exposed rock. No shoreline. No weathered mountains delivering minerals into shallow seas. Just water layered over water, until pressure becomes so enormous that the water changes phase into high-pressure ice. Ice 6. Ice 7. Ice 10. Ice that can exist at temperatures where ordinary ice would have melted instantly, because pressure forces the molecules into structures impossible at Earth's surface. At the bottom of such an ocean, there may be no familiar seafloor at all. The liquid layer may be sealed away from the rocky interior by high-pressure ice, cutting the ocean off from the geochemical interactions that may have helped life begin on Earth. Or, in some cases, heat and pressure may create exotic interfaces we do not yet understand. GJ1214b and K218b have both been discussed in the broad family of water-rich or volatile-rich sub-Neptune worlds, though neither is a confirmed Earth-like ocean planet. Their interiors remain hidden beneath thick atmospheres and hazes. We do not know whether their water, if present, is a habitable ocean, a supercritical fluid, a deep mantle layer, or something else entirely. That is the problem with ocean worlds. They sound familiar because they contain water, but water, under enough pressure, stops being familiar. Mini-Neptunes and sub-Neptunes. Here is the category our solar system forgot to include. Planets between Earth and Neptune in size. Larger than rocky worlds. Smaller than ice giants. Often between roughly 1.5 and 4 Earth radii, with rocky or icy interiors wrapped in envelopes of hydrogen, helium, water vapor, methane, or other volatiles. We have nothing like this around the Sun. There is Earth. Then there is Neptune, almost 4 times wider. Between them, nothing. But in the galaxy, that missing size range is everywhere. The Kepler census showed that small planets between Earth and Neptune are among the most common worlds we have found. The solar system has a gap exactly where the exoplanet catalog is crowded. That should disturb us more than it usually does. It means the most common kind of planet may be a kind of planet no human has ever seen up close. What do they look like? We do not fully know. Some may have solid surfaces buried beneath crushing atmospheres. Some may have no clear surface at all, only a gradual transition from gas to supercritical fluid. Some may be water-rich worlds wrapped in hydrogen. Some may be rocky cores under atmospheres so deep that sunlight never reaches anything resembling a ground. A planet can be common and still be almost completely unknown. The galaxy may be dominated by worlds that do not exist in the system that produced us. Ice giants. Uranus and Neptune are often called gas giants in casual language, but they are not simply smaller Jupiters. They are ice giants, planets with smaller hydrogen-helium envelopes and interiors rich in water, ammonia, methane, and other volatile compounds. Not ice in the sense of frozen surface snow, but planetary ices, materials that formed far from the young sun and now exist under enormous pressure. Inside Uranus and Neptune, water and ammonia may form deep, electrically conducting layers. Methane may break apart under pressure, allowing carbon to rain downward as diamond-like material. Their magnetic fields are tilted and offset in ways that suggest interiors far stranger than a simple layered sphere. These are not gentle blue marbles. They are laboratories of high-pressure chemistry wrapped in cold hydrogen atmospheres, with winds faster than the strongest hurricanes on Earth and interiors we have only begun to model. Our solar system has too. The galaxy probably has countless more. Gas giants and hot Jupiters. Gas giants are familiar because Jupiter exists. Huge planets dominated by hydrogen and helium. No solid surface. Atmospheres that deepen into liquid-like layers, then into metallic hydrogen under pressure so extreme that ordinary intuition fails. Worlds whose visible clouds are only the top skin of structures far deeper and stranger than weather. Jupiter and Saturn are the calm version. Other systems revealed the violent version. Hot Jupiters. Gas giants orbiting so close to their stars that their years last only a few days. Some are closer to their stars than Mercury is to the Sun. Many are tidally locked, with permanent day sides roasted by stellar radiation and night sides that never see direct light. Their winds can move faster than bullets. Their atmospheres can swell, escape, or be stripped away by ultraviolet radiation. They should not have formed where we find them. That is the key. A gas giant needs cold outer regions to gather ices and build a massive core before capturing hydrogen and helium. So hot Jupiters likely formed farther out and migrated inward, dragged by gravitational interactions with the disk or scattered by other planets. A hot Jupiter is not just a planet. It is evidence that an entire planetary system rearranged itself. A Jupiter that moved inward would not travel politely. It would disturb smaller planets, eject worlds, force collisions, clear orbits, and rewrite the architecture of the system. The planet itself may be calm in a telescope catalog. Its existence is the fossil of chaos. Superpuff planets. Some planets are not violent because they are hot or fast or close to their stars. Some are violent because they seem almost impossible to hold together. Kepler 51b is one of them. It has only a few times Earth's mass, but a radius more than half that of Jupiter. Do the calculation, and the density becomes absurdly low, far below water, lower than many foams, in the same broad territory that inspired the nickname Superpuff. A planet with the gravity of a small world wearing the silhouette of a giant. For a while, the popular image was irresistible, a planet less dense than cotton candy. That phrase is not a scientific model, but the shock behind it is real. These worlds are so distended that their atmospheres dominate what we observe. The solid or dense interior may be much smaller, hidden beneath an enormous envelope or high-altitude haze that makes the planet appear larger in transit. Why do they exist? Possibly because their atmospheres are filled with photochemical hazes. Possibly because they are young and still swollen from formation. Possibly because low gravity allows hydrogen-helium envelopes to extend to extraordinary altitudes. Possibly because our measurements are catching them in a temporary stage before stellar radiation strips them down. Whatever the answer, superpuffs prove that a planet does not need to be solid, compact, or sensible. A planet can be almost all atmosphere, a shadow with a core somewhere inside it. Chthonian planets. Now reverse the superpuff. Take a gas giant. Put it too close to its star. Leave it there for millions or billions of years. Let ultraviolet radiation heat the upper atmosphere. Let atmospheric escape carry hydrogen and helium away into space. Let tidal forces, stellar wind, and possibly collisions or formation history remove what once made the planet large. Eventually, the envelope is gone. What remains is the core, dense, exposed, orbiting naked where a giant used to be. That hypothetical remnant is called a Chthonian planet, named after the Greek underworld, a world stripped down to what was once buried. TOI 849b is one of the strongest candidates for this kind of story. It is roughly Neptune-sized but unusually massive, with a density suggesting that it may be the exposed remnant core of a former gas giant, or a giant planet that somehow failed to acquire or keep its massive atmosphere. The details remain debated, but the image is powerful because the physics is real. A gas giant can be stripped. A planet can lose its sky. A world can become the fossil of its own destruction. Pulsar planets. The first confirmed exoplanets did not orbit a living star. They orbited a corpse. PSRB 1257 plus 12 is a pulsar, a neutron star about 1,000 light-years away. It spins roughly 160 times per second, sending beams of radio emission into space with clock-like precision. Around it are planets, small worlds confirmed in the early 1990s, before 51 Pegasi b, before the hot Jupiter era, before exoplanets became a routine part of astronomy. That fact should still feel strange. The first confirmed planets beyond the Sun were not found around a star like the Sun. They were found around the remnant of a supernova. How did they get there? Maybe they survived the explosion. Maybe they formed afterward from fallback debris around the neutron star. Maybe their history is more complicated than either simple picture. What is clear is that they exist. Rocky planets orbiting a dead stellar core, bathed in radiation, timed by pulses from one of the densest objects in the universe. Not every planet needs daylight. Not every planetary system begins with a living star and ends when the star dies. Some begin after the death. Circumbinary planets. Some planets have two suns. Not metaphorically, literally. They orbit binary stars, two stars locked in mutual orbit, rising and setting in pairs, pulling on the planet with a gravitational rhythm more complicated than anything in our solar system. The habitable zone around such stars moves and changes. The amount of light can vary as the two stars eclipse and circle each other. The sky would not have one central clock, but two. Kepler found several of these worlds, proving that planets can form and survive around binary stars despite the gravitational complexity. This matters because many stars in the galaxy are in binary or multiple systems. The Sun is single. That, too, may be less typical than we once assumed. Rogue planets. No star at all. Free-floating planetary mass objects drift through interstellar space with no parent star, no sunrise, no year, no orbit around anything except the galaxy itself. Some may have formed inside planetary systems and been ejected by gravitational encounters with giant planets or passing stars. Others may have formed more like tiny failed stars, directly from collapsing clouds too small to ignite fusion. We detect many of them through gravitational microlensing, a brief brightening of a background star when the invisible planet passes in front of it and bends the light with its gravity. The galaxy may contain huge numbers of rogue planets, perhaps one per star, perhaps fewer, perhaps more. The uncertainty is large because they are dark, cold, and difficult to find. But some rogue planets may not be dead. A massive rocky world or mini-Neptune ejected with a thick hydrogen atmosphere could trap internal heat from formation and radioactive decay. Beneath that atmosphere, pressures could be high enough and temperatures warm enough for liquid water to exist. A world without a sun, in the darkness between stars. Possibly warm, possibly wet, possibly not empty. Hycean worlds. The word is new. Hydrogen plus ocean. A Hycean world is a proposed class of planet larger than Earth but smaller than Neptune, with a hydrogen-rich atmosphere over a global ocean. The hydrogen atmosphere acts as a greenhouse blanket. The ocean below, if conditions are right, could remain liquid even where an Earth-like planet would freeze. This category matters because it widens the search for life. For decades, the imagined target was simple: rocky planet, sun-like star, Earth-like orbit, thin atmosphere, surface ocean. But Hycean worlds suggest another possibility: life under hydrogen skies, on planets larger than Earth, around red dwarfs, in conditions that do not resemble home but may still permit chemistry to organize itself. K218b is the famous candidate. It is a sub-Neptune in the habitable zone of a red dwarf, about 120 light-years away. JWST observations have detected methane and carbon dioxide in its atmosphere, supporting the possibility of a hydrogen-rich world with chemistry unlike Earth's atmosphere. There have also been tentative claims of dimethyl sulfide or related sulfur chemistry, molecules interesting because on Earth, DMS is mostly associated with biology. Tentative is the important word. The signal is debated. Alternative analyses can explain the data without an ocean and without life. Instrument systematics, atmospheric modeling, and overlapping molecular features all matter. K218b may be a Hycean world. It may be a gas-rich mini-Neptune with no habitable surface. It may be something that does not fit either simple picture. But the fact that we can even ask the question is extraordinary. The first serious atmospheric hints connected to possible life beyond Earth may not come from a second Earth. They may come from a world with no analog in our solar system. Retrograde and misaligned planets. Our solar system looks orderly. The planets orbit the Sun in the same direction. Their orbits lie mostly in the same plane. It gives the impression that planetary systems are built like flat, calm clockwork machines. Many are not. WASP-17b is one example. It is a huge, inflated gas giant with a mass less than Jupiter's, but a volume many times larger. It orbits its star in a retrograde path, backwards relative to the star's rotation. A planet does not usually begin that way. Retrograde and highly tilted orbits are scarce. They suggest gravitational violence, planet-planet scattering, close encounters, quasi-litive cycles driven by distant companions, tidal evolution after orbits have been twisted into extreme shapes. Other hot Jupiters orbit at angles of 30, 60, even near 90 degrees relative to the spin of their stars. Some move over the poles. Some move backward. Some systems look less like clockwork and more like the aftermath of a gravitational accident. The planets are calm, now only in the sense that the crash is over. Their orbits remember it. What the catalog means. More than 6,000 confirmed exoplanets. Thousands more candidates. Statistical extrapolations suggesting hundreds of billions of planets in the Milky Way alone. And in that population, rocky worlds, lava worlds, carbon-rich worlds, ocean worlds, mini-Neptunes, sub-Neptunes, ice giants, gas giants, hot Jupiters, superpuffs, Chthonian remnants, pulsar planets, circumbinary planets, rogue planets, Hycean candidates, retrograde giants, and likely categories we have not yet named because our instruments have not become sensitive enough to reveal them. The universe makes all of them, without preference, without design, without any obligation to make worlds comfortable, stable, breathable, or even understandable. It applies disk chemistry, gravity, radiation, migration, collision, evaporation, tidal forces, magnetic fields, and time to an enormous variety of starting conditions. The results are not exceptions. They are the catalog. The solar system gave us the impression that planets are orderly things. Rocky close in, giants farther out, everyone on circular orbits, everyone behaving according to principles that feel almost sensible. Every other solar system has been teaching us that this impression was an artifact of our ignorance. A sample size of 1. Step outside on a clear night and look at any star. There is probably at least one planet there. Maybe several. Maybe a rocky world. Maybe a hot Jupiter skimming its star. Maybe a lava planet raining minerals onto a magma ocean. Maybe a superpuff larger than Neptune and lighter than Sense. Maybe an ocean world with no continents, no shoreline, and no sky visible from below. Maybe a rogue planet that used to have a sun and now drifts alone between the stars. Maybe something stranger than all of these, something our categories will fail to describe when we finally see it. The variety of worlds in the galaxy is not bounded by what our solar system prepared us to imagine. It is bounded by what physics permits. And physics, it turns out, permits almost everything. The solar system is not the template. It is one page of a catalog that goes on for longer than we have yet read. And most of what is in that catalog is insane.